Hi everyone, welcome to the Royal Meteorological Society's Early Career Conference. Thank you for joining us today. This is the joint session for Meteorological Applications and Dynamics. So I'm the chair for the Dynamics session. My name's Amethyst. I've just finished a degree in Environmental Science at the University of Manchester, and I'm going to be starting a PhD in Leeds. And for the next session, we've got Ben.
Yeah, so I'm the co-chair for the Meteorological Applications session, which is the final two talks of this session. My name is Ben Pickering. I am a final year PhD student at the University of Leeds studying weather radar and applications of it.
So for the sessions, we're doing 10 minutes of a talk followed by 5 minutes of questions. So when we're nearing to the 8-minute mark, I'll just come in and say there's 2 minutes left, just so we keep to time. So I'm just going to introduce our first speaker for the dynamics session. We have got Akshay, if you'd like to turn your webcam on.
This for the introduction. Hello everyone, I am Akshay Deoras. I am a PhD student at the Department of Meteorology, University of Reading. And I'm in my second year of PhD and I'm researching the Indian monsoon. So today I'm going to talk about a few stuff that I have been doing over the last few months. The title of my presentation is Comparison of the Prediction of Indian Monsoon Low Pressure Systems by Subseasonal-to-Seasonal Prediction Model. So we have got a data set that is known as the S2S prediction project, which I have used for my work. So I'll just quickly go through my slides. So monsoon low pressure systems are important synoptic scale tropical disturbances, and they bring a lot of rainfall over the Indian subcontinent. Primary genesis of these systems occurs over the northern parts of the Bay of Bengal, and typically we get around 13 low pressure systems every summer. And these systems modulate intra-seasonal rainfall variability. So if you see this plot that I have from Hunt and Fletcher 2019, so that basically shows how much precipitation that's happening in summer is attributed to these low pressure systems. So you see pretty much these systems form here, or the northern Bay of Bengal, from where they propagate towards India, and they bring a lot of rainfall, which is like up to 80 to 90% is attributed because of these systems. The point is why we are doing this. So the motivation is that these low pressure systems have triggered at least 4 catastrophic floods in the Indian subcontinent in the last decade, and these 4 floods in Uttarakhand, Tamil Nadu, Gujarat, and Kerala have been really massive, killing many people and destroying and damaging a lot of things. Lots of things have been investigated, like there are lots of papers which talk about the structures of these low pressure systems, but we really don't know how much we can predict them, like in how advanced we can really issue some skillful forecast, and that's where this PhD project comes in. So what like I said, so I'm using the S2S data sets that basically contains reforecast and near real-time ensemble members from 11 global centers. And for verification, I'm using ERA interim. So these reforecasts from the S2S data set, they have different configuration, like different model resolution. So ensemble members, number of ensemble members are also different. They have different reforecast frequency, lead time, etc. And that's very important because this varying configuration really helps us to explore and look from different perspectives, like how, for example, forecast lead time influences the skill of predictions and things like that. And these models have a common reforecast period of June to September 1999 to 2010, which I'm using for my analysis. That's just a quick table that shows how this data set is. So you have got these different models. You have got model from Bureau of Meteorology Australia. You have got a model from the European Centre for Medium Range Weather Forecast. That's the ECMWF. You also have got UKMO. You have got JMA, KMA. That's the models from Japan, Korea. And they have different reforecast time. They have different resolutions. You can see different number of reforecasts as well. Their reforecast frequency is different. Some of them are coupled to ocean. Some of them are not. So that's really interesting because that gives a lot of different ways of looking at this stuff. So how I'm doing this, I'm using a feature tracking algorithm to track low pressure systems in S2S models, and I'm verifying them with ERA interim. So here's a schematic that shows how this is being done. So let's say after applying the feature tracking algorithm, you get a monsoon low pressure system in black, like you can see here. And let's say you have got a track from ERA interim that's in blue. So when I consider, like, how do I really match these two tracks? So for that, I consider the first 2 days of these two tracks, and I see whether these two tracks are separated by a certain distance. That could be anything like 200 kilometers, 300 kilometers, and so on. And if that condition is satisfying, then I say that, okay, this is a matched pair, and I go for further analysis. So here are some quick results. That's the first result that comes in. So what you see here is you have got forecast lead time on the x-axis and position errors there on y-axis. So that's basically the difference between these two tracks at each lead time. So what you see, as we would expect, because these tracks, like the track from S2S and the track from error entrum, they begin very close to each other initially, and then they diverge. So forecast error grows with time, increasing forecast lead time, like you can see. And the interesting stuff here is you have got differences among different models. So the CMA model that comes in from the China, so that basically has got the lowest scale. It has got a highest position error. So that's the curve here in blue, and it goes up to 1600 kilometers by the end of this forecast window. So that's not a good model for sure. Whereas some models like the UKMO, JMA, and KMA, so that's the UK Met Office models from Japan and Korea, so they have relatively low position errors. That means they have higher scales. When we consider the intensity bias, like differences between the intensities of low pressure systems in the S2S dataset and the error interim dataset, so we see similar situation. There are again differences in different models. So here each curve shows different models. Like for example, magenta curve shows the Bureau of Meteorology Australia model. What you see here is most S2S models overestimate the intensity of low pressure systems, that they have a positive bias. But some of them, like for example, the HMCR, so that has a negative bias that underestimates the intensity. While a few models I have not written here, but there's a JMA model which has the lowest bias. And that really gives us a very nice idea of how good these models are in terms of their predictions. Final two bits. So now how do you really understand if a model is statistically reliable or not? And to get that, we have something called as the ensemble spread error relationship. So what this basically means is that when you have an ensemble forecast, so it needs to be broad enough to consider different possible forecast states, so that your observation lies within a forecasting sort of an envelope. That is the rough meaning of ensemble spread error relationship. So what you see here, I have got different models, all the 11 S2S models, and I've got 3 curves. So I've got a curve in black, I've got 2 curves in red. One is a solid red and one is dashed red. So the black-red curve shows you control error, that is the error in control run of individual models. The red one, solid red, shows you mean error. The dashed red shows you spread. So spread is effectively the sort of difference between individual tracks and a mean track. So that again gives you a range of how much variation is there in a model when it comes to track forecasting. So 3 models, the ECMWF, UKMO, and BOM models, they have the best ensemble spread error relationship. That is, these 2 curves are close to each other. So the solid red and dashed red, these curves are close to each other in these 3 models. So there you can say that these models are statistically reliable. However, the HMCR model, which comes from the Russian side, that has the worst ensemble spread error relationship, and that's really bad because you can't really use this particular model for really getting some statistically reliable forecast. And then you have got, just get it back. Right. And then the ensemble mean provides an advantage over the control for some models, except the HMCR again. And for the intensity, so this one is for the position of low pressure systems, but now this one shows for the intensity. So what you see here, again, the same stuff, 11 models, you have got 3 different curves. So for the intensity, there are larger differences between ensemble mean error and spread than the position, which is understandable because when it comes to track predictions, you can really predict these tracks quite well because they're dependent on the large scale circulation. However, intensities, they are just going to depend on several localized features, which it's not possible to really accurately sort of forecast in these particular models. So for the ensemble spread error relationship, you have larger differences, like I said, between the ensemble mean error and spread and the position. Again, the UKMO and the ECMWF models have the best spread error relationship, whereas again, the HMCR model has the worst. The ensemble mean provides an advantage over the control run for some models, such as the ECMWF and UKMO. But that again gives a very nice idea of how much you can use these models to really forecast low pressure systems. So quickly summarizing this, because this is just a very tiny aspect of my first part of PhD project. We have just submitted a paper to weather and forecasting. So I would encourage you to have a look at it if you want to really understand more aspects and get into more details. Quickly summarizing, so there are large differences in the scale of S2S models for the intensity and position of monsoon low pressure systems that we have seen quite clearly. The CMA model has the highest position error. Remember, it goes up to 1600 kilometers by around 15 days lead time, whereas the UKMO, GMA, and KMA models have the lowest position error. So you can really use these models for better forecasting of low pressure systems. Most S2S models overestimate the intensity of monsoon low pressure systems for all lead times. That's what we have seen. The ECNWF and UKMO models have the best ensemble spread error relationship for the intensity as well as the position of low pressure systems. However, the HMCR model has the worst. Most models are under dispersive for the position error of monsoon low pressure systems. So this is a very interesting point. So what I mean by under dispersive is that the spread in these models is not sufficient to really consider the actual observation. So that's what under dispersiveness here means. And that's quite common among different ensemble forecasting systems. So most models are under dispersive for the position error, and models are more under dispersive for the intensity than the position, which is again because intensity is really hard to sort of predict as against the sort of position error. So that's it for now. I am happy to go. Yeah, thank you for attention. I'm happy to answer a couple of questions if you have. Thanks.
Good timing. So Ben's got a question. Would you expect the ECMWF model to have an advantage in this verification?
Yeah, that's a nice question because if you have got ECMWF and error interim, that effectively comes out of ECMWF, so naturally there will be some sort of advantage to that. And I think it again comes back. You also have got one question like, is it worth repeating the analysis with error 5 data or something like that? So I would expect error 5 to have kind of similar results to error interim. Probably the best way for some sort of additional verification would be to go for other reanalysis data sets such as GRA55 or MIRA. We plan to do that, but as of now, I don't have any time scale like when we would do that. But yes, for sure, there will be some sort of bias towards sort of error interim when you have ECMWF ensemble forecasting system.
Okay, great. And a question from Alex: have you considered how this model skill might change at different times during the monsoon and over timescales of variability?
That's a good question. So I am going to do that in my third sort of chapter, where we are really going to look at, I wouldn't say model scale as such, but we're really going to look at how these systems vary on the intra-seasonal time scale. That's what Alex is asking, like how different June is compared to September. And over other timescales variability, yes, we are also going to look at it from the intra-annual perspective as well. But I think for that, you need to come to the next year's conference because I won't be in a position to sort of better answer your question at that point of time.
Okay, and I just had a question as well. I noticed some of your models coupled the oceans and some didn't. Did you notice a significant difference between those that coupled the oceans and those that didn't?
For this particular one, there's still not that much difference because when you have this ocean coupling situation in place, I think that is going to really matter the sort of structure of monsoon low pressure systems more, because you have got tropical cyclones. If you know, tropical cyclone has got a warm core and then it has a lower core, it has a cold core, which is kind of opposite when it comes to sort of these monsoon low pressure systems. So we expect that factor to be more influential in impacting the structure of these systems rather than the prediction, because like these systems, they do spend quite a lot of time over the land than the ocean, which is completely different than tropical cyclones, which like enjoy spending a lot of time over the ocean than the land. So I think that sort of answers your question.
Okay, great. If there are no more questions, I'd like to thank you, Akshay, for your presentation.
Right, thank you.
And our next presenter is Michael. If you'd like to turn your webcam on. Great.
All right, good morning. My name is Michael, and then I'm presenting on the topic, the climatology of mesoscale convective systems in Southern West Africa. I'm a second-year PhD student in the University of Leeds. So mesoscale convective systems are one of the most devastating high-impact weather systems that affect Southern West Africa. If you look at the satellite image that you have on your screen, it shows typical convective systems that affected the region on the 1st of June 2020. And if you analyze this, you realize that these systems are unlike the synoptic scale frontal systems that bring rain here in the mid latitude. These systems are rather relatively smaller in scale, and so pose a great forecasting challenge because numerical weather prediction models struggle to represent these systems in the region. So forecasters in the region, a better understanding of the climatological characteristics of this system is very important for accurate forecasting. And so I address three main research questions in here. And the first one is to look at the climatology of the environment of these mesoscale convective systems that affect the region, and then to look at the reasons why some of these storms live longer and propagate faster than others, and then how extreme MCSs in Southern West Africa are characterized. Now, Juan Guetta has actually he has introduced a tracking algorithm that and has tracked MCS data and made it available. So I take this data and then first group this data into the four main classification that was introduced by Tomasini in 2006. And so the plots that you see here on the slide is just an example for the year 2007, the distribution of storms based on their lifetime and speed, because the classification was done based on the lifetime and speed of the storm. So you can clearly see how he separated short-lived, slow-moving systems from long-lived, slow-moving systems, then short-lived, fast-moving systems from long-lived, fast-moving systems. And so the next thing that I did was, in order, because actually, if you look at West Africa, different parts of West Africa are affected with storms of peculiar characteristics. And so to clearly pick out and understand why we have these peculiar storms in the different regions, I have separated the regions. I have separated the Gulf of Guinea from the North Atlantic, the Congo area from the Sahel, from Southern West Africa, and the coast. So the plots that you see here is basically the total number of MCSs that were tracked in between 1998 and 2007 over these regions that I am investigating. So let's look at the first question. What is the climatology of the thermodynamic environment associated with the MCSs in Southern West Africa? So the first thing that I decide to show here is to see how these different storm classes are related to their average sizes. So on the x-axis, you have the different storm classes, the short-lived, slow-moving, long-lived, slow-moving, short-lived, fast-moving, long-lived, fast-moving. And the first thing that is very obvious when you look at this plot is that you realize that MCSs over Southern West Africa, that is the orange line, are normally greater and larger than those in the Sahel, the red line. And also, one striking thing that you see clearly is that the long-lived, fast-moving storms are dominantly larger than the short-lived, slow-moving systems. And so we say that storms live longer when they are larger, and then larger MCSs mostly propagate faster, and most smaller MCSs are short-lived and slow-moving. So now the question is, why do we have this behavior? And so to understand this, I decide to plot the number of MCSs and then overlay the surface winds, the 925 hectopascal winds, and also decide to show regions where you have orography, that is elevation greater than 400 meters above sea level. And so it is clear that most of the regions that you have a lot of storms are actually the regions where you have large convergence happening. And also, these are also regions where you have orography associated with them. So it is very important then to try to understand for the different sub-regions of West Africa, how this convergence zone is associated with the storms with the type of storm that you have in the region. So in this next slide, I have plotted divergence for storm composites for each of the regions. So on the top, I have oceanic and coastal storms like the Gulf, the North Atlantic, and the coast at the top. And then at the bottom, we have land storms like the Congo, the Sahel, and Southern West Africa. Now, the first thing that you realize is that for the oceanic storms, it is clear that the main location of the storm appears to be collocated with the region where you have the strong convergence zone. But when you look at the land, if you look at the plots at the bottom, you realize that the location of the storm is not necessarily where you are having the strongest convergence. Actually, if you look, for instance, at Southern West Africa and Sahel, you realize that the strongest convergence zone is actually happening north of the main storm location, which is actually the ITD region. And so it becomes interesting to ask then, where is the convergence associated with the storm over the land? Are they located at higher levels? So to try to investigate this, I have shown on this slide a vertical transect along the longitude of the main storm location. And so if we look at the Sahel and Southern West, or if we look at the land where we are trying to find where the convergence is, we realize that the main convergence that is associated with the land MCSs are actually happening between 800 and about 700 hectopascal levels. So the storms, unlike the oceans, if you compare to the oceans, the convergence associated with the storms are happening at the surface. But when you look on the land, they are actually happening at kind of mid levels. And also, one other thing that you see is that oceanic storms are associated with stronger vertical velocities compared with land MCSs. And so in this next slide, I have shown, I have taken a vertical profile through the storm location. And we realize that even though from the previous slide, we see that oceanic storms are associated with very strong vertical velocities, we see that the ones these are rather not as deep as the land MCSs. And the land MCSs are deeper because they are associated with higher cape. And that is the reason why the land MCSs are deeper than oceanic MCSs. They are, other interesting things on this plot, but I'll not get into them now. So let me look at this question of the reasons why we have some storms are living longer and propagating faster than other storms. So to answer this, I have this question that what controls MCS speed, the rain rate, and their lifetime? So I pose this hypothesis that strongest and most long-lived storms occur in strongly sheared environments. So to investigate this, I plot a distribution of lifetime against speed for all the storms, and I show this for the mean size compared to the brightness temperature, the rain rate, and the wind shear. Then what you see clearly is that the colder storms are storms, they are long-lived, and these storms are also storms that have larger sizes associated with high rainfall rate, and interestingly also high wind shear. So we see that a strong shear seems to result in large storms deep storms, and also to some extent high rainfall rates. And these storms are also long-lived. So the question is, what are these long-lived storms associated with? Is the African easterly wave playing a role here? So to try to see the role the African easterly wave is playing, I decide to plot the meridional winds associated with the storms, and then I separate the short-lived storms, the ones at the top. The short-lived storms are extreme A storms from the long-lived storms. They are the ones at the bottom, the extreme B storms. And I investigate the conditions. If you look at the x-axis, the conditions 2 days before the arrival of the storms to 2 days after the arrival of the storm. Now, if you look clearly, you see that long-lived storms are living longer because they are associated with the African easterly wave. If you focus on the North Atlantic extreme B storm, for instance, you clearly see that before the arrival of the storm, you have strong northerlies in the region. Then you have the storm arriving before you have southerlies following. So you clearly see that these long-lived storms are associated with the African easterly wave, and then the storm is located just ahead of the African easterly wave trough for all these regions. And so I conclude by saying that the convergence zones over the oceans and coast coincides with the mean storm location, but for the north of the mean storm location over the Sahel and southern West Africa. And then the mean convergence associated with Sahel and southern West African storms occur just around the mid-levels and not the surface. And although you have stronger velocities associated with oceanic storms are not as deep as the land storms. The land storms are deeper because they have higher cave. And then we also see that the long-lived storms are mostly associated with the African easterly wave. And then we have the clear difference between short-lived and long-lived storms also here. Thanks so much. Any questions?
Ben had a question in the chat which was similar to mine. It says, you have some great results. How will you feed these through to the NWP and forecasting centres to make sure the improvements are made in this region?
Yeah, so one thing is that I personally actually worked with the Ghana Meteorological Agency, so I work with forecasters, and then one thing I experienced is that the forecasters actually do not trust the NWP product as far as predicting convective systems is concerned. They trust it for large scale, just to look at the synoptic scale features, but they don't trust it for convection. And so with these peculiar features that has been identified with the different storms, it is clear to guide forecasters, because the forecasters make most of the detect where convection is happening, mostly based on experience and other characteristics of the storm. So once they are getting a clearer picture of how the different storm categories are behaving, it guides them in a very good prediction.
Okay, so your research is guiding forecasters directly.
Exactly, for more accurate prediction, because there's prediction over the region has been a great challenge.
Okay, and just a quick one. Alex says, what physically causes larger, more long-lived storms to be associated with strong wind shear?
Okay, so in West Africa, actually, one thing that's happening is that mostly on the if you look at the climatology, on the surface, you mostly have southwesterlies on the surface from around 95 to 850, the monsoon flow, and then at mid levels you mostly have this strong easterlies, the African easterly jet. So the interaction between these surface southwesterlies and then the mid-level jets creates that strong shear. And most of the storms that are influenced by this jet and this are the storms that are long-lived, and they are more deeper, and because you have the monsoon flow is actually supplying moisture into the storm, and then the together with the jet is trying to create suitable conditions for more deeper and stronger storms. So that is the reason why those storms, because they have enough moisture and they are more deeper, they are able to live longer than the ones that are associated with lesser shear. Yeah.
Great, thank you. Thanks for answering those questions and for a great presentation.
Yeah. Thanks.
So our next presenter is Shaun.
That's not right.
Hi.
Hello. Okay. Thanks, Amethyst. Yeah, so I'm Shaun. I'm from the University of Bath. And here today, I'm going to talk to you about the tides of the Antarctic Mesosphere and Lower Thermosphere. So let's see what time it is. Cool. So atmospheric tides, why do we actually care about these? So as global circulation models aim to push higher up into the atmosphere, we need to be able to represent the upper layers. So a lot of the tropospheric models, stratospheric models doing quite well. But as they push up and go into the mesosphere, lower thermosphere, so we're talking from about 60 kilometers all the way up to maybe 140 to even 600 kilometers, we need to be able to represent a wide variety of waves. So these can be tides, gravity waves, or planetary waves. And each one of these has a different kind of characteristic that they need to represent. And the MLT is quite dominated by atmospheric tides. So that's a key thing that they need to get right so that they can then predict what's going to happen correctly. So what are atmospheric tides? Well, we can see them in lots of different variables. They appear in temperature, they appear in wind. And using meteor radars, we can look at the wind in the mesosphere and lower thermosphere. So here we have some time height contours, which describe the winds over a few days. So this is 2 weeks in April 2009. And the clear thing we can see in these is this repeating pattern. So there's a lot of things. So you see the red stripes going up and down. So each one of these features happens twice a day. So you can see that these are periods of around 12 hours. And superimposed onto this, there's 24-hour tides as well. And this just shows how much the wind field in this area is actually dominated by these tides. So in order for models to really actually represent what's happening here, they need to have these in there, or they're not really representing it. So what are the atmospheric tides I've talked about? So these are solar force oscillations. These have been caused lower down in the atmosphere, where the chemical species are excited, and they force waves to rise and grow in the atmosphere. And as density decreases in the atmosphere, these waves grow exponentially and cause periodic oscillations in the wind. So what I've had here is a nice periodic oscillation. These are just a time series of the winds at 90 kilometers for 2 days. And you can see if we add on these lines here, so it's a bit messy, but bear with me. So you can see there's a 12-hour tide line. So this is just a 12-hour sign fit to these data in orange. We have a yellow line, which is the 24-hour tide, and then combined 12-hour and 24-hour tide. So the reason I put these on is because tides have periods that integer fractions of solar days. So this means we have a 24-hour tide, we have a 12-hour tide, and we have 6, 8, 6, 4, etc. As they get smaller. The biggest ones at the location we're looking at, which is Rothera, in the Antarctic, are the 12 and 24, which is what I've shown here. So if we add these together, we can actually see that it represents the blue dots, which is the wind, pretty well. Now, the only things that aren't represented are probably gravity waves or influences of planetary waves that aren't represented in these fits that I've done. So we can see our tides are dominating the MLT. So how are we going to compare our models to the observations, the actual atmosphere? So we're going to use 2 GCMs. So this is the whole atmosphere community climate model, which is WACCM, and the extended Canadian middle atmosphere model, which is ECMAM. And we're going to compare these to a meteor radar on Rothera, the British Antarctic Survey's base on the Antarctic Peninsula on Adelaide Island. So the study year is going to be 2009 because it's the year we have available for both models and the radar. So what do we actually see in the observations? So if we look at the observed tides, so these are the ones from the radar. If you just take the first one, these 2 first boxes, A and B, these are time series of the tidal amplitudes at 90 kilometers. And the bold lines are a moving average, and the other ones are a 4-day sliding average. And we can see that for both components, the 12-hour tide is the largest, and the 24-hour tide is a bit smaller. They're both quite variable, which is good. It means that they have day-to-day variability. And if we look at the semi-annual oscillation that we can see, so we've got 2 peaks. We've got an April and a September peak in the 12-hour tide. So we move down to the next panels. We can see that there's quite a strong increase in amplitudes at higher heights at the equinoxes, which is showing that there's some kind of forcing going on there. Now, if we go down to the 24-hour tide, it's consistently smaller than the 24-hour tide and doesn't have the same semi-annual cycle. It has an annual cycle, increasing in the summer months of December, January, and February, because we're in the southern hemisphere here, as opposed to the 24-hour tide, which has this semi-annual cycle. So if we compare it to our first model, which is Wacom, we can use the same thing. So this is looking at the 12-hour tide and the 24-hour tide. We can see that for the start on the time series, the 24-hour tide is much larger all year round. Well, not much less. So it's larger all year round, which is opposite to what we had in the observations. We can also see that the semi-annual cycle that was apparent in the radar is actually not apparent in the model, which is something that we need to take away. The amplitudes that we see are roughly similar, but they're not the same. And finally, the 24-hour tide is showing the same kind of intensification in December, but it is not the same amplitude. It's much larger. Our final model is ECMAM. We can only use the 24-hour tide from this due to the sampling of the data from, the sampling of the output. But we can see that this annual cycle is actually picked up in this as we saw in the radar. It's intensifying in December, January, and February. So that's good. And we can say that it does actually follow it, even though the amplitudes are a bit smaller. So to look at this more closely, we look at these profiles. So these are profiles of height versus amplitude. And the radar is in the blue line, and either side we've shaded it with the standard deviations. This represents the variability within the month, and plotted as well we have the Wacom model for the 12-hour tide, and we can see that the observed tidal amplitudes grow dramatically with height. So if we look at April, for example, this is growing from nearly 2 meters per second to 30 meters per second over 20 kilometers, which is very, very large changes. And this isn't represented by the models. So the amplitude growth with height isn't represented in Wacom as well as in the radar, because the radar is growing large. Wacom is being quite consistent as it grows. However, you can see that lower heights is actually doing pretty well in amplitude. So it's doing really good. It's going reasonable agreement in the lower heights, but as these amplitudes are growing, it's getting less and less good. Okay, and the next one is the 24-hour tide. We can see that if we have all three models on, so we have the green line has now been added on, which is the ECMAM model. And we can see that for a start, this is not as dramatic growth with height as we saw in the 12-hour tide. This is much more shallow, which is great because that's what ECMAM shows. So ECMAM is doing pretty well as a model to represent these tides. It's growing in a reasonable agreement. It's not growing much, which is what we saw. Compared to Wacom, we can see that this is systematically larger. Although it does have the same amplitude growth with height, it doesn't have the same amplitude. So you can see months such as August, we're almost 10 meters per second larger than as we actually observe. So that's a problem that we need to actually investigate. So what could be the cause of these differences? So a good thing to look at is the monthly mean winds. These give an indication of what wave species are actually in the models, as well as in the observations we see. So if we look at the top two panels, these are the zonal in the left column and the meridian in the right-hand column. And if we just focus on the zonal for now, we can see that the radar shows quite strong eastward winds. So these eastward winds are in red in the left, and you can see that throughout the year, it's mostly eastward, with a few blops of westward in the summer months of December, January, and February. Compared to the models, we can see that Wacom actually produces these two nodes of westward flow pretty well. However, in the winter months, in the June, July, August, we can see that this is westward flow coming in. And the same in ECMAM, where we have the blobs of westward flow as well as the overall westward flow in the middle. So obviously, something's going wrong. Now, it's been proposed that something called secondary gravity waves can actually cause models to miss having this eastward flow in them. So if we take a look at secondary gravity waves, so what these are these gravity waves that grow from maybe some surface or convective source, and they break higher up in the atmosphere. When they break in the atmosphere, they can then ripple and cause more waves, and you can then get tertiary waves and other things. So we're going to call these non-primary gravity waves. And these can exert body force on the atmosphere, causing it to have more drag imposed on it. So this is a drag in inverted commas, as there's not actually something dragging on it. It's just Newton's third law applying. So if we have a mountain here, the wind hitting against it, the momentum is transferred up in the atmosphere and pushes back. So it has a drag on the atmosphere. And this could be an issue why the models aren't representing this well. So if we look at actually a model that includes this, so if we are looking at 60 degrees south, so the vertical line of 60 degrees south, and looking at above 0.01 hectopascal, so at the top, On the left-hand side is a model that includes secondary gravity waves, and we can see there is this eastward flow that we observe. And on the right is one without the secondary gravity waves, where we do not see this eastward flow, we see westward. So this is a really big indication that that's what's causing it. And the other thing, it could be non-linear coupling between waves and planetary waves, and this causes the amplitude to beat with periods of the planetary wave, which means there's influence from this that isn't being picked up in the model as such. So to conclude, atmospheric tides dominate the MLT region, with the 12-hour tides, especially so above Rothera. The tidal amplitudes increase greatly over the height range we observe. So this is from about 5 to 30 meters per second, which is quite large. Wacom shows good agreement with the 12-hour tide below 90 kilometers, and also in some of the in October to December, you're getting quite good agreement in those lower portions, and it's systematically larger than the 24-hour tide. ECMAM, oh, it's moving. ECMAM shows generally good agreement for the 24-hour tide. It doesn't show the same amplitude growth, which is great, and the lack of secondary gravity waves in the models may be a cause for these differences. So thank you very much for listening, and hopefully this will be published this year. I'm getting the paper ready for you all to read. So I'll be ready to answer any questions you have.
Thanks, Shaun. So the first question is from Ben again. He says, do these tides have any known effect on the formation of noctilucent clouds, or is that
noctilucent? Okay, so noctilucent clouds are caused by meteor dust. So this is exactly the stuff that we're measuring when we look at the waves. So at the moment, it's a really good time to look at noctilucent clouds. You can see them. I've seen these pictures above London, which is really actually quite low down to be able to see them. So that's really nice. So this doesn't actually have an effect as such. So the noctilucent clouds more come out when the mesosphere is cooling. So at the moment, it's a really important time for this because we're getting into that kind of time of year when there's Brewer-Dobson circulation is increasing, so that the heat is transferred away from the polar mesosphere. So these tides don't have a direct effect as such, but they do enhance it.
Okay, I had a question as well. My main question, I was basically going to ask, what do you think the main differences are between the model and the observations, but you kind of answered that. So I just wanted a little bit of clarification on it. So at one point you were talking about the radar, and then another point you were talking about the gravity waves. I'm just trying to piece it together in my head.
Yes, of course. So when we measure the radar, we measure the winds. So you just measure a value for the zonal and the meridional wind. Okay, so we then use, to extract the tides, we use those sine fits. So we extract the amplitudes from those. And what's left over that's residual is always caused by some kind of external forcing. So the tides are there, they're oscillating, but then every so often there'll be some kind of wave pass through the wind, and that will cause it to move in a certain direction and increase the flow in that way. So when I talked about gravity waves, to be more clear, it's these external factors that causing the winds to be either more southward, more eastward as the wave progresses through our observation filter. Because obviously when we use a radar, you're looking at, in meteor radars, you look at like a big ring-shaped area of the sky. So as you're looking into that, measuring what's happening, as a wave progresses through this, you'll get diversions from what you actually think is going to happen. And because the atmospheric tides are so large in this bit of the atmosphere, you actually can say they're going to dominate the wind field, and anything else is going to be something extra that's going to be in that. It's just that when you measure something, you're measuring the total. Okay. You can't just measure the individual contributions.
Okay, that's great. Any more questions? I'll give you a couple of seconds just to quickly type those in. No, I think that's fine. Thank you, Shaun, for that presentation.
Thank you very much.
So the last presentation from the climate session is Tim.
Okay. Hi, I'm Tim. I'm also at the University of Bath, doing a PhD in atmospheric gravity waves. And my presentation is titled, Can We Wave Goodbye to Parameterisations? So special thanks to my supervisors, Corwin Wright, Nick Mitchell, and Neil Hinley, for their helpful insights. So I suppose the first important question to ask is, what actually is a gravity wave? Well, put simply, it's any wave occurring between stable fluid layers where gravity is the restoring force. So if you just think about if you throw a rock into a lake, then the ripples that you get emanating outwards, they're just gravity waves. It's a combination of gravity and buoyancy that's causing the wave that you see. And so, any kind of wave that you get like that is a gravity wave. In the top right-hand picture, you can see a mountain with a lenticular cloud above it. And so what's happening here is it's like a rock in a stream. You have the the air kind of hitting the mountain and being forced upwards. And then you can get gravity waves kind of propagating upwards into the atmosphere. So gravity waves are really important. They play a key role in the transfer of energy and momentum through the atmosphere. And they have important implications for aviation safety, climate models, and numerical weather prediction. One important point to make is that they're not gravitational waves. Those are completely different. That's to do with black holes and pulsars and things. So this is gravity waves, not gravitational waves. So we generally split them into two types, orographic gravity waves and non-orographic gravity waves. And orographic gravity waves generally have a narrow spectrum of horizontal wavelengths. This is basically because mountains are essentially motionless relative to the Earth's surface, and non-orographic gravity waves are more kind of complicated with different sources. So with orographic gravity waves, the drag on the atmosphere is given by Elias and Palm's first theorem. And if you look at the equation, the left-handmost term is the upward momentum flux, and the rightmost term, so kind of the rho naught U prime W prime, that is the zonal eddy momentum flux. And this equation is essentially saying that gravity wave absorption tends to decelerate the mean flow, that's U naught, to the wave phase speeds, that's C. And if you think about the kind of the mountain situation, although the initial stress on the mountain caused by the air moving across it happens at the surface, due to Newton's third law, so kind of a reaction force to that, the drag on the atmosphere kind of occurs right the way up through the atmosphere. So it's sort of action at a distance, if you like. And then non-orographic gravity waves, there's kind of a wide spectrum of horizontal wavelengths with all kinds of sources like convection, jet stream emission, fronts and wind shear zones, and really kind of a wide range of scales, so from 1 kilometer all the way up to 1,000 kilometers. So what's the current approach in models? Well, for waves with large wavelengths, they can generally be easily resolved and verified by satellite measurements, so we don't have too much difficulty with those. But as we get down to kind of smaller scales, we have to start using hyperdiffusion schemes to dampen these smaller scale waves out, generally for numerical stability purposes. And as we get down to the subgrid scale, we have to start using parameterisation schemes. And it's really important that we do that, because if we don't do that, then we don't end up with a realistic middle atmosphere, which is quite important. That's related to the kind of stuff that Shaun was speaking about. So let's go back to kind of the basics. Look at a primitive example of a parameterisation scheme. And the envelope orography is a good example of this. And essentially what you're doing is you're artificially enhancing orography and using the topographical height variance at a grid scale to infer the gravity wave momentum flux. So this is good in some ways. It solves some problems, but it does interfere with radiative processes in the planetary boundary layer, and it can fill in some basins and mountains, which is far from ideal. So over the years, we've gradually kind of evolved in time, and we've improved our schemes, and we've been imposing constraints on, say, the downward eddy momentum flux and the Richardson number, allowing wave saturation and wave reflection at different critical levels, and more recently, taking into account nonlinear effects and boundary layer parameterizations. So there's been this general kind of improvement in gravity parameterization schemes as model resolutions have improved and our observations have improved. So I'm very interested in the UTLS region. That's the upper troposphere, lower stratosphere. And the main reason for that is given by Palmer in 1968, where he says gravity wave breaking preferentially occurs in the boundary layer and in the lower stratosphere. So this is kind of a really important area. And I've said their contributions to zonal eddy momentum flux, that's that term that I was talking about before on the right-hand side, that's often greatest in the UTLS. So that gravity wave drag that's happening all the way up through the atmosphere, that often happens primarily in the UTLS. Now, one of the problems is that it's quite hard for satellites to observe this due to the tropopause, so really kind of a sharp change in the temperature gradient. And so spectral analysis, if you want to try and capture gravity waves, is quite difficult. It also means that research potential is quite good in terms of improving model resolutions and new satellite capabilities. I mentioned the Aeolus, which is a really exciting new satellite, which I'll talk about in a bit. But firstly, I'll talk about the IARGOS system, which is basically just a data set from a 26-year-long data set from commercial airliners, primarily used for atmospheric chemistry monitoring purposes, but it's really got a rich amount of data that we ask the question, can we use this to study gravity wave flux in the atmosphere? Are these planes flying in the right area, the UTLS? Are we able to see what's going on? So just looking at some brief kind of plots, looking at the distribution of these flights. On the right hand side, you can see that they're flying generally between 200 and 300 hectopascal. So this is the perfect place to look at the UTLS region. This is obviously where they're kind of the cruise flight is. But if you look at the left hand plot, you can see that there are some issues with data. Obviously, we have good coverage over the North Atlantic in some areas, but in other areas there's poor or even zero coverage. There's some places the planes just aren't flying at all. So it's got some good things and some bad things with it. If we've got a paper that's coming out soon, so if you want to know any more information about this, I'd recommend looking at that paper when it comes out in the next month or so at the bottom there. So onto Aeolus, which is the really exciting satellite, and this was approved in 1999 and was launched in August 2018, so quite a long time. You can insert a joke here about European bureaucracy if you want, and it costed a lot, 481 million euros, so really expensive. And it's the first wind LiDAR in space, and that's the thing that's really exciting about this. It's the Aladdin instrument, which is the really kind of the novel thing about the satellites. So what is the Aladdin instrument? Well, it's a Doppler wind LiDAR. It's probing the lowermost 30 kilometers of the atmosphere, and it's providing profiles of wind, aerosol, and clouds along the orbital path. Profile measurements are derived from the Doppler shifted signal, so along the line of sight of the laser as it's pointing down, and it's measuring the wind speed in that way. So this is a really new technique. It's never been done before, and it's absolutely perfect for measuring in the UTLS. So here is just some raw Aeolus data. It's kind of really new data, and yeah, the question we're going to ask is, can we see gravity waves using Aeolus? So if you look at the right-hand plot, and you can see in red the track of the satellite going from north to south. The laser points out the right-hand side of the satellite, so pointing in the west direction. And you can see on the left-hand side these kind of strong negative values. That's a strong westerly zonal wind, which is what you'd expect. So it's a good sanity check. We've got a nice jet that we can see. And so can we find gravity waves in this data? Can we use some techniques, find some perturbations to find some gravity waves? Well, what I've done here is I've just highlighted some phase fronts that we can see using the Aeolus data minus some Error 5 data, which has been smoothed. And we can begin to see the beginnings of some gravity waves coming out. And what I'm trying to do is I'm trying to develop some tools and along with my group to bring out these gravity wave parameters. We want to know the gravity wave wavelengths. We want to know the gravity wave amplitudes. And this kind of plot here is the kind of plot I want to be able to create, where we've got a map showing the variances. And what we expect to see here is areas where there's lots of gravity wave activity would be experiencing a higher variance. So this is an example of the kind of plot that I want to make when we've improved our techniques. So just a summary on what I've gone through. Gravity waves play a key role in atmospheric dynamics. They resolve well at larger wavelengths. But as we get down to smaller wavelengths, to the subgrid scale, we have to start using parameterization schemes. And we are better at parameterizing orographic gravity waves than non-orographic gravity waves, something I didn't mention. But I went through some of the schemes for orographic gravity waves. With non-orographic gravity waves, due to all the different sources, they're much more complicated. So it's a lot harder with those. And the UTLS region is a key area for improvements. So if we can measure the UTLS area, if we can get measurements from there, then we can improve our models, we can improve our measurements, and that's is really the direction we want to go in. So I suppose the question to ask is, can we wave goodbye to parameterisations? And I would say no, not yet. I think they're very useful, but we are reducing our reliance on them as our observing capabilities and model resolutions improve. And I think that bodes well for the future. So thank you for watching.
So we've already got a few questions in that. Ben says it looked like on the Aeolus plot that one observation is made over 8 to 7 kilometers. Is that a problem for resolving UTLS gravity waves?
Right, that's a good question. So with the Aeolus data, there's different stages with it. So the Aeolus instrument is measuring kind of individual observations at quite high resolution, horizontal resolution, but then it aggregates those up into measurement, which, as you say, is around 87 kilometers. So for measuring waves where the wavelength is of that order, that's great. But as we get down to gravity waves that are shorter than that, obviously we're going to have some problems. So you're absolutely right, it is a problem. And until we have measurements at that really high resolution, we're always going to have a great difficulty in measuring waves with really short wavelengths. And I suppose that's where the parameterization schemes kind of come in to kind of help out. So yes, yeah, that is a problem, but it's something we're slowly improving on.
Does waves have anything to do with seismic waves?
That's an interesting question. So with seismic waves, I would say that gravity is not the restoring force. So obviously you have an earthquake, say, and it's just a rarefaction. You have kind of the restoring force is not gravity, right? With a gravity wave, it's the air is being pushed up, or the fluid's being pushed up, and then it's kind of oscillating up and down to do with buoyancy and gravity. So they are different kinds of waves. I don't think that a seismic wave would cause a gravity wave in the atmosphere, but yeah, I don't know whether anyone else would know about that. So.
Okay, and I just had one question as well about the impacts of the work. So what kind of real life impacts are you trying to have with this work?
Yeah, so right at the beginning, there are a few that I mentioned to do with kind of aircraft turbulence and things. If you can understand gravity waves, they're often a cause of severe air turbulence and clear air turbulence. So that's obviously a real life impact. We can forecast gravity waves. If you just model gravity waves better, then we can improve aviation safety. And of course, then there's just the model improvements. If we can improve our measurements of the gravity waves, then we can represent them in models better and have better forecasts for the future. And obviously climate models as well use these kind of parameterisations, so that's another kind of effect. So.
Okay, that's great. So if there are no more questions, I'd just like to say thank you to Tim for a great presentation.
Thank you.
And that concludes the first half of this joint session. So that's climate done, and I'm just going to pass over to Ben now to do the meteorological applications.
Thank you very much, Amethyst. Now is on to the meteorological applications session. We have two talks in this session. First up is Mark Prosser. Good morning, Mark. I'll give you a warning at 8 minutes, okay?
Great, thanks.
Right, the floor is yours.
Thank you very much. So my name is Mark. I'm from the University of Reading, where I study clear air turbulence. And specifically in this project, we're looking at using real clear air turbulence accidents and incidents that happened in the sky over the past 20 years to evaluate the skill of clear air turbulence diagnostics. It's funny speaking with the headphones on. Sure. So clear air turbulence is already a big issue for the aviation industry. In the picture, you can see that this plane here has unfortunately managed to lose one of its engines. And this happened in 1992 when it was flying over the Rocky Mountains. There are sort of various figures for the financial cost of clear air turbulence to the aviation industry. But apart from the financial cost, there's also a human cost, because in a severe clear air turbulence incident, you can be hospitalized, and people are frequently each year. And something like 23% of all aircraft accidents and incidents are due to invisible forms of turbulence. And these are particularly a problem because they cannot be sensed by the plane or forecast very accurately. So quite often it's a case of just inadvertently encountering them and having to ride them out, basically. So while it can be quite bad and people can be hospitalized, usually, well, in fact, no one is ever, hopefully yet, killed as a result of clear air turbulence, except if you're in a light aircraft. But a commercial aircraft, it's fine. So we have some ability to forecast, but it's not great. There are a lot of times when we say there's going to be turbulence and there isn't, times when we say there isn't going to be turbulence and there is. And so here's just to give you an idea of the sort of thing that can happen if you're involved in a severe turbulence encounter. Most of the ones that people encounter, the more frequent ones are the less serious ones. So while clear air turbulence is already, sorry, just to say, you can say clear air turbulence, you can use the acronym CAT. CAT is already a problem for the industry, but it's likely to become even worse with increasing levels of climate change. So Storer et al. Did some work where they ran a climate model with an RCP 8.5 scenario, which is kind of like the business as usual climate change scenario where no mitigation takes place. And they compared it with a pre-industrial control. And then on top of that, they applied turbulence diagnostics to the climate output. And here is the difference between the two model runs. And you can see that there is about a 300% increase in clear air turbulence on average. And there's even more around the jet stream regions where it's closer to 500%. And just to say, this figure here is at the 200 hectopascal level where planes fly. However, there is a bit of uncertainty associated with this figure, which I'll explain in a bit. So clear air turbulence at the moment cannot be simulated in models because the processes which generate it are subgrid scale. So what we do is we use clear air turbulence diagnostics, which work by taking the variables that are explicitly output by climate models and relating them to the probability of turbulence occurring. However, there's many on the market, so to speak. Here is a table of 21 of them, which we have been looking at in this project. And I mentioned the uncertainty in the previous plot. Just go back to it. This is because this is a plot that is made up of a diagnostic mean of those 21 clear air turbulence diagnostics. So depending on which individual one you apply to the climate model output, the distribution of turbulence ends up looking different. So what we ideally need is a way to evaluate the skill of these different clear air turbulence diagnostics, and in particular, which of them are skilled at detecting not just clear air turbulence in general, but aviation affecting clear air turbulence. And so this is where my project comes in, the idea being to use real accidents and incidents that occurred in the atmosphere to validate or test the skill of these different 21 diagnostics. Okay, so I'm using the ERA 5 reanalysis dataset in this project. And ERA 5 is extremely large because of its high resolution. And so first step in my method is to calculate what the distribution of these 21 diagnostics looks like in ERA 5. Now, because it's so large, I have to take a sample, and you can see this blue rectangular box, and this is where I take a sample. This box here is for the year 2016, and it is over 10 pressure levels, 200 hectopascal to 300 hectopascals where planes fly. So once I have calculated the distributions of the different 21 diagnostics, I then have to then work out what do these diagnostic values correspond to in terms of a percentile for that diagnostic. So then I have to scour the internet and any resources that I can find to find actual clear air turbulence accidents and incidents. And I've managed to find 87. So once you've found one that you can be reasonably sure is clear air turbulence, you have to be able to get enough data on its date, time, latitude, longitude, and altitude. And if you don't have all of those bits of information, you can't use the incident. And so then for each of these events, you calculate the diagnostic value for each of the 21 diagnostics and the percentile value. And then you take, so once you've got a percentile value for all 87 of those events or incidents, you then take an event mean across all 87. And if the diagnostics were to have zero skill at all, we would expect the mean of their event means to be around 50%. However, this is not quite what we find. We find the event of their event means are above 50%. So here you have, so here's a table with the results and the percentile, and the diagnostics are ranked in terms of skill, with the best scoring diagnostic at the top and the worst at the bottom. And then this graph here is, thank you, shows the same results, just in a graphical form. So we have 18 out of 21 are above the 50th percentile, with 7 over the 66th percentile. So we have some are doing better than others, and the natural question to ask is why this might be. So the best scoring diagnostic 12, the magnitude of a horizontal temperature gradient. So a lot of clear air turbulence in the atmosphere happens in the vicinity of the jet stream. And the jet stream is generally stronger when there is a greater horizontal temperature gradient. And so it is perhaps not so surprising that diagnostic 12 has done well. And also deformation is flow deformation is quite known to be the cause of much clear air turbulence in the atmosphere. And all 7 diagnostics with a flow deformation term in them are in the top half of our rankings. Some diagnostics didn't do so well, especially those with the Richardson number, which was a bit surprising. I've made a histogram of each of the diagnostics, so you can see which percentiles the 87 events fell in. Skip that. And this is similar to what I've already said. So thank you. Any questions?
Thanks very much, Mark. We do have some questions. I have some of my own, but first we have Amethyst, who asks, how will these results be fed into the aviation industry to improve safety?
Yeah, so I guess at the moment we're looking at this in a climate perspective. And so, for example, so if the aviation industry is to be able to adapt to climate change, I feel it's got to have a sort of clear idea of what the future is going to look like in terms of clear air turbulence, where the clear air turbulence is, when it's likely to occur. And at the moment, in the figure you saw, we took a mean where it sort of assumes that each diagnostic is as good as every other. And so if you have, so now that we have an idea about differential skill between the diagnostics, we can create another mean, which can perhaps give us a better picture, a more accurate mean with different weightings for aviation affecting CAT.
So do you have channels to sort of take these results and provide them back to the industry?
So my supervisors have quite a few links with the industry. So yes, I think we do basically, but through my supervisor. Yeah.
Cool. And then the only other thing I wanted to ask was just on the point of, you said that these sort of processes with clear air turbulence cannot be resolved explicitly. I just wanted to know how high of a resolution would you need? Are we close to approaching the resolution needed, or is it way beyond what we could ever achieve?
I don't know if ultimately it's beyond our capabilities, but I think we're not anywhere close to it at the moment.
So it's like sub 100-meter scale almost.
Well, yeah, because I guess this, yeah, you can turbulence goes down to the Kolonov scale. So I'm not sure to what extent you need to go down to that level, but yeah, certainly not at the scale we've got at the moment.
All right, well, if there's no more questions, then I think we'll wrap that up. Just to let you know, Tim has responded to one of your queries from before, so just want to make sure you see that.
Thank you very much.
Yeah. All right, thanks very much, Mark. So our next speaker is Alicia Gleason from Lake Street Consulting. This is a pre-recorded talk, but I believe Alicia is here live with us to answer questions at the end. So we will start that now.
Forecast dry spells for Oxfordshire.
thanks for that. We are running a little bit ahead of time, so we have plenty of time for questions. I believe Alicia is here with us, if you're there.
Hello.
To answer any questions that we have. Good morning.
Morning.
Okay, so we have a couple of questions. Chris is asking, do you intend to compare your regimes to the North Atlantic weather regimes?
Yeah, so I did that for, the typical or the classical Euro-Atlantic winter weather regimes. So I just did that originally to make sure that the clustering was working. That was kind of my test. So yeah, and from using the k-means method, I was able to get out the NAO, the Scandi blocking, and the Atlantic ridge. So that was one of the tests that I used.
Mm-hmm. Thanks. And then I had a question myself, which is similar to the one that Josh is asking. Did you consider clustering methods like hierarchical? What made you choose the k-means method for doing the clustering?
Yeah, so originally I'd actually did a principal component analysis. That's kind of done a lot in the literature. And I did that by itself and then did k-means after using PCA. But the results, when I tried to get the classical winter regime, that they weren't very intuitive. So I was actually reading a paper, which I have a reference for, and they had tried doing it it was Falcana et al., but they did the same kind of idea, but they did it on the full field data set was the EOF. So that's where I got the idea from. And that was when I was able to actually get out the classical winter regime. So that's I had confidence then in that method. So that's why I chose to use that one.
Mm-hmm. And then just to put up Josh's other question, how did you choose how many clusters to look at? Which is always the interesting one.
Yeah, so I use this, I kind of use very often is the elbow method. So where you plot your number of clusters against the inertia and where it starts to drop off. So yeah, and it was around 4, so that's why I tried. And I tried it for other amounts as well, just to see, but 4 was what made the most sense.
Great, thanks very much.
Mm-hmm.
If we don't have any other questions in the chat, then I think we can wrap this session up here. So thank you very much to all of the speakers in both of these sessions, some great talks that we've had there. So now we have a social refreshment break and the photography competition that'll be on another channel. And then after that, we have at 11:30 poster session C, which will be chaired by myself and Jinghua Li. So I hope to see you all there. Thank you all for joining, and thank you to all our presenters again.